Hi everybody, Physics Ninja here. Today what I want to do is I want to look at motion graph problems. And what I have for you are 10 problems. Yes, 10 problems that we're going to work through together. Now what I suggest is that when I first introduce the problem, I suggest you pause it after I read the problem, try it out on your own, and then watch the rest of the video to get the solution. All right, it shouldn't take you more than 3 to 5 minutes for each problem. All right, so we're going to deal with everything that has to do with motion graphs. So we're looking at position, velocity, and acceleration graphs versus time in these problems. We're asking you to analyze going from velocity to acceleration, going from position to velocity, and so forth. So by the end of this, hopefully you have a better grasp on how to solve motion graph problems. These are important for physics exams, okay, in order to be successful in physics exams. So like with all my videos, if you like it, give it a thumbs up. Consider subscribing to my channel. It's the best way to support what I do. All right, let's get started. All right, question 1 shows a figure down here of position versus time, and we're asked several questions. The first part says, which curve shows the motion of an object with constant acceleration? Well, how do you define acceleration for a position versus time graph? What do I need? This is my definition of acceleration. It means a change of velocity over a change in time. That's the definition. So we need a velocity final that is bigger than a velocity initial. That's what we need. And again, these are vector quantities. So it can't be, for example, a curve B. Curve B has a constant velocity everywhere. And how do I know that? Because the slope is constant, right? The velocity is simply the slope of a position versus time graph. So B has a constant slope, can't be that one. How about choice E? E is also a constant slope, right? The slope is 0 for this case, so that can't be it. And then we're left with 3 curved choices. So the first thing you have to know is that if the shapes are curved like an A, C, and D, then there is acceleration because the velocity changes. Okay? Let's look at D, for example, right? D here has a velocity. All you do is you draw a little slope over here. This value represents this initial velocity. If I look at some other point down the road here, I have a final velocity. And look what I have. This is steeper than the initial velocity. So in curve D, the slope is getting bigger, which means I satisfy this. So D here has positive acceleration. Okay. A, on the other hand, and also C, they have slopes that get smaller. Look at choice C. If I draw a slope over here, it's some positive value. And look at over here, the value is still positive, but it certainly is smaller. So in this case, we don't have positive acceleration. All right, what about question B? Says, with constant positive velocity. So we got to be very careful when we read these questions, right? So they say constant positive velocity. How do you get velocity from a position versus time graph? Again, the velocity is given by the slope. That's what I wrote right here. And we want a constant positive slope, right? I can just replace the word velocity by the slope. And for that one, you can clearly see it has to be choice B. Everywhere if I draw a slope, I get the same value. All right, so this guy here is choice B. Which curve shows an object that is at rest? So if something is at rest, it means that its velocity at every single point should be equal to 0. That means that the slope should be equal to 0 everywhere. And that clearly has to be this choice E right here, right? Because it's flat for every single time. So E here is the correct answer for question C. And the last one, question D, says we have negative acceleration. So negative acceleration is the opposite of the first case that I considered. Negative acceleration means that the slope is going down. So let's have a look at a couple cases here. Look at choice A. Here you have some velocity that's negative, right? But look what happens. It's becoming more negative, right? It's steeper, but it's going down steeper. Okay? So that means that this final velocity is actually less than the initial velocity. How about choice C? Choice C is the same thing. It's just kind of looks a little bit different, right? But it's still kind of a case where the final velocity is going to be smaller than the initial velocity for every single point. So in this case, we actually have two answers. We have A is a case where the final velocity is smaller than the initial velocity. And also, what else? Curve C. So we have two choices with negative acceleration. All right, hopefully that one makes sense to you. Again, for that negative acceleration, we require that my final velocity is less than the initial velocity. And in that case, this equation right here is going to give us a negative number. All right, let's go to the next problem. All right, problem 2 says a little bit different now. Now we're given a velocity versus time graph. So we have to be careful, right? Which curve shows a motion with constant positive acceleration? So constant positive acceleration if you're given a velocity versus time graph. Okay, so how do you get acceleration if you have a velocity versus time graph? Then right away, it's simply the slope of the graph, right? So what we want is a constant positive slope of velocity versus time graph. That's all we need. So which curve has a constant positive slope? It has to be choice B. See, the blue line has a constant slope everywhere. Question B says, with a positive acceleration that is decreasing with time. Okay, so it's positive, but it's decreasing with time. So which curve over here which depict that? Again, it has to be something that is curved, right? Because it's changing with time. So let's look at choice C over here. Let's look at that one. If I draw a slope over here, I have a positive acceleration. If I go a little bit further in time, I still have a positive slope. But what is that slope doing, right? Compare these three little lines over here. The slope is actually getting smaller, right? So it's decreasing with time. So actually for choice B over here, I think the best choice would be the curve C. All right, how about question C says, which curve shows the motion of an object with no acceleration? So if I have no acceleration here, it means my acceleration is 0. So what would that mean? That means that the only way I get 0 here is if V final equals to V initial. Well, that here has to be choice E, okay? Choice E is the best answer for that one because there is no slope. The slope is 0 everywhere along the motion here. All right, and the last one is question D says, which curve here depicts the motion with positive acceleration that is increasing with time? Okay, increasing with time. So let's have a look at D over here. D, if I plot different slopes at different times, look what the slope is doing. Again, the slope represents the acceleration. The slopes are always positive, and that's what we require here. And the slopes are always getting bigger. Okay, see this last orange line is steeper than the first one that I drew over here. So for this last one, it's really curve D that is the best. What about curve A? What is happening to that case? Well, in that case, the slope is always negative, right? But there are no choices here where they said that the acceleration would be negative, okay? The slope is changing, but it's always negative in this case. So that doesn't represent any of those cases. All right, for each of these graphs here, we want to know if the velocity at time t2 is bigger, less than, or equal to the velocity at time t1. Question B says, well, what about the speed? Okay, so how do we compare the speeds at time t1 versus t2? Remember now, these are graphs are changing in time here. They have some curved shapes. So when we're looking at velocities, we're really looking at the instantaneous velocities at all of those times. And the way you calculate the instantaneous velocities is by looking at the slope of the graph at that specific point. Okay, if you wanted to do this with calculus, it's really how you take this slope of the position versus time graph. So we're comparing 2 points over here. We're going to be comparing T1 and T2. Let's look at the slopes. Here's a little mini slope at T1. And look at here on this curve. The slope is almost flat here at the top. Okay, so clearly that the slope is smaller here at T2. Right, so for choice A, this is also question A, graph A, and choice A for the velocity. The velocity at t2 is less than the velocity at t1. Now they want to know something about the speed. How do you calculate the speed? If you know the instantaneous velocity, the speed is simply the magnitude of the instantaneous velocity. All right, so that's just something to remember. Because this instantaneous velocity could be positive or negative, right? But if we're looking for the speed is a scalar. We simply want to know the magnitude of that vector. So in this case here, I would also say that the speed at t2 is going to be less than the speed at t1. All right, what can we say now about graph B? Again, if I go and I graph little slopes, I have a slope here and I have a slope here, and clearly the slope everywhere on this orange line is going to be the same, right? So here we'd say that the velocity at t2 has to be equal to the velocity at t1. Let me go ahead and just add my vector signs here just to keep this neat. How about the speed? Also, the speed at t2 has to be the same. All right, so I'll just write speeds are equal. All right, how about the last one here? It's not the last one, I'm sorry. Choice C down here. So what do we have over here? Well, this is a mini slope here at time t1. That's the velocity, and you can see we'd get a negative value over here. And then what do we have here? We have a positive value, right? It is positive here, and the velocity here is negative. So clearly the velocity at t2, right? The velocity at t2 has to be bigger than the velocity at t1, right? So velocity at t2 should be bigger than the velocity at time t1. Now the speed, on the other hand, only worries about the magnitude, right? For example, this guy, if I had numbers on the graph, I may get -5 meters per second, right? It's pretty steep. Over here for this guy, I may get a positive value, but it looks like the slope is pretty small. I may get +1 meters per second, right? Again, the sign here tells me something about the direction of the velocity, the direction of the motion. For the speed, I don't really care about all that, right? So really, if I look at the speed of t2, it has to be less than the speed at t1. Because I'm only worried about the magnitude of those slopes. All right, let's look at the last one here. Graph D, if I draw a mini slope here, I get a small positive value. Let's just assign a value to it, +1 meters per second. Let's go ahead now and do the slope at T2. Look what I get. I get a larger negative value, right? It's steeper than it is over here. So I may get -2 meters per second. So what do we get here for the velocity? We get that the velocity at time t2 is going to be less than the velocity at time t1. You have to take the sign into consideration for the velocity. If I'm looking for the speed, on the other hand, the speed would be simply taking the absolute values over here. And clearly the speed of time t2 has to be bigger than the speed at time t1. Okay, because of the definition of the speed only requires the magnitude. All right, question 4. You're driving a sports car that accelerates uniformly from 50 to 70 miles per hour in 9 seconds. We want to know which velocity versus time graph describes the velocity of the car. So one of the key words here is uniform acceleration. And also look at here, like at time 0, we start at 50. So look at some of these graphs. Some of these graphs start right here at 0, right? At time 0 here, I'm at 0. So it definitely can't be that one. Look at this one. This one here also starts at 0. That can't be, that doesn't make sense. Look at the last one over here. What's going on with the velocity here? Here the velocity is actually getting smaller, right? So that's not what's going on. I'm actually speeding up here. So you can get rid of that one. So we're left with 2 cases. They both have a little bit of an offset here. Okay, so that's okay because at t0 I want to have 50 miles per hour. The next case is I accelerate uniformly. What does this mean? If I have a velocity versus time graph, the acceleration is the slope. So what do I want? I want the acceleration to be uniform. I want the slope to be uniform. So it must be this guy over here. This here has to be the one. This one has a slope that increases, so the acceleration is changing with respect to time. All right, so that's it for question A. Question B says sketch a position versus time graph showing the position of the car in the first 9 seconds. All right, so what would this look like? So let's see. Again, this is just a sketch, position versus time. We're initially at position 0. So I'm going to go right here. So at time 0, I'm right here at position 0. Now, how do I depict this in this figure over here? Now, one thing to remember is that at T0, I need to have 50 miles per hour. Remember, how do I represent this velocity here on a position versus time graph? This here must represent the slope. Okay? What about at 9 seconds? Let's say this here is 9 seconds over here. What I need over here is I need a curve that is sloped with a slope of 70 miles per hour. So I don't know what that's going to look like, but it has to look something like, right? This curve has to do something like this. And then the slope constantly sloping like this, constantly changing. It should look like a parabola. I've done a bad job of tracing that parabola, but let's look at over here. Here I have a slope, okay? And the slope here would be equal to this 50 miles per hour if I had the right units. The slope over here is steeper, right? So here the slope must be 70 miles per hour. Okay, and we should have a parabola here, so the speed is constantly changing. The velocity is increasing from 50 to 70 in a uniform way. So let me just write that down, a parabola. All right, that's it for question 4. All right, here's question 5. The position versus time diagram of two cars traveling in parallel lanes is shown. First question says, are they ever side by side? So what does this mean? If they're going to be side by side, it means they have to be at the same position, okay? So where are these cars at the same position? This is a position versus time graph, so clearly it has to be where the lines intersect with each other, okay? So that looks like at time equals to 1 and also at time equals to 9 seconds, right? The positions of the cars are the same. Question B says, are they traveling in the same direction or moving in opposite direction for part of the time? Well, let's have a look. Car B's always have a positive velocity, right? The slope is always positive everywhere in its motion. Look at car A. Car A has a positive slope over here. However, look at the slope is getting smaller, and right at about here at 6 seconds, right? The slope here is 0, which means that the velocity of A has to be 0 over here at the top. And then what happens? The slope gets negative, right? The slope over here is a negative value, which means it's traveling in the opposite direction. So it's like this time interval from t equals to 0 to 6. They are the same direction. And then after that, from time equals to 6 through 10 seconds, right? Car B is traveling in one direction, positive slope. Car A has a negative slope, so this here would be opposite direction, okay? All right, how about question C says, are they ever traveling at the same velocity? How do you get a velocity versus time for each one of these cars? So what you have to think about is the velocity word. The velocity word means the slope. Now, is the slope ever the same? Well, let's have a look. The slope of B is always this positive constant value, right? Is there anywhere on this curve A that we have an instantaneous slope equal to that of car B? So it has to be positive, and I'm going to say it's probably right around here. Oh, that's kind of a little too thick. Let's thin that down a little bit. It looks like it's probably right around here. If I draw a tangent to the curve, it's probably similar to car B. So I'd say right at about t equals to 5 seconds. The velocity of car A is roughly that of car B right here, right? We have the same slope value. All right, how about D? D says, when are the two cars the farthest apart? Farthest apart means the distance between them. Well, that is simply looking at the position. Where are the two curves the most spread out? Okay. Again, you're looking at this distance right here, and it's probably right about at 5 seconds. Notice they are far apart here. It looks like at 5 seconds it might be a little bit bigger. And there's also some separation over here, but clearly here they're not very far apart. Here they're not very far apart. They're getting farther apart here. Let's say 5 seconds is probably close enough, given that information on the graph. All right, question E says, sketch the velocity versus time for each graph. So we want to make a different graph. If you're given position versus time, how do we plot the velocity versus time? So let's go on the next page and do that. All right, so let's start with car B. It's probably the simplest to do. Let me just change my pen. Okay, so for car B, again, we look velocity versus time. Well, the velocity here is just the slope, and the slope is always the same value. So on a velocity versus time graph, it should look flat. Try to draw a straight line here. Now, car A, we said, let's analyze the motion of car A. Car A, we said at about 6 seconds, the slope was 0, right? So the slope here should be 0 over here. Look at the slope of car A at the beginning. It's a positive value and it's pretty big. Okay. Then what happens? The slope is actually getting smaller as you approach time equals to 6 seconds. Now, the way that we do that is probably just going to use a straight line here to keep it as simple as possible. And then what happens to the slope? It changes sign. It becomes slightly negative and becomes more and more negative. So all I would do is I simply keep going, continue the curve like this. And that is what the velocity of versus time would look like for car A and for car B, the orange line here. All right, great. Let's go to the next question. All right, for question 6, we have which graphs of Vx versus t best describe the motion of an object? The first question says we want a positive velocity and an increasing speed. All right, so we want it to increase. We're given velocity versus time. So if we want the speed to increase, there better be some kind of slope. So it can't be A or B. Now we want the speed to increase. So look at this one. This one definitely has a speed that increases, right? The velocity is getting bigger and the magnitude of the velocity is getting bigger. And we have positive velocity everywhere. Okay, so that one is okay. So let's at least write choice C over here. What about these other ones? Do we have positive velocity for this one? No, we don't for choice D, right? The velocity is under the line, so the velocity is negative, okay? How about choice E? E, we have positive velocity, yes. However, we have a decreasing speed, right? The magnitude of the velocity is 0 over here, right? And it's some positive value at the beginning. So it's really only graph C that satisfies the first one. Question B says a positive velocity and 0 acceleration. All right, which graph has 0 acceleration? Again, the way you get acceleration from a velocity versus time graph is looking at the slope. So we want the slope here to be equal to 0. So we really only have 2 cases where we have 0 slope, and we want to have positive velocity. So the only one with positive velocity would be graph A. Choice C says constant non-zero acceleration. So which graph basically has an acceleration that is not 0? So whichever one here has a slope that's not 0 is going to have a constant non-zero acceleration. And the slope is constant everywhere, right? So definitely a choice C is okay. What else? Nothing wrong with choice D. The slope is constant and it's not 0. And also choice E, right? So we want a constant slope. Constant non-zero slope. All right, great. And the last one says a speed decrease. All right, we can rule out this one. This speed is the same everywhere. Speed is increasing for this one. All right, now we got to be careful. So which one is the speed decreasing? Remember, here it's 0 and here it's 0, right? Here it's some value, right? Some positive value. It could be 3 meters per second, right? So that's definitely decreasing. So definitely I agree that E has a decreasing speed. Here, look what the velocity is doing. The velocity here is going to be some negative value. Let's just give it a value here, minus 1 meters per second. So that means that the speed at this point here would be the magnitude of that, right? So it would be 1 meter per second for the speed. So that speed is actually increasing for choice D. So we really only have graph E that satisfies that case. All right, indicate all the graphs that represent an object moving with constant velocity. So let's be careful here. We have position versus time graphs. We have velocity versus time graphs, and we also have acceleration versus time graphs. How do we indicate constant velocity? So for position versus time, remember, how do you find velocity, right? The velocity represents the slope of the graph, okay? So what we're looking for is a constant slope, and the only one with a constant slope is choice A, okay? The slope is negative, but it's constant, so that's good. If I have a velocity versus time graph and I want to have a constant velocity, well, the velocity has to be the same everywhere, right? So clearly this one here has to have constant velocity. These other ones here have velocity that is different for every moment in time. It cannot be constant. And the last one is acceleration. How do you find the velocity, or how do you show an object has constant velocity from an acceleration versus time graph? Okay, remember, if you have an acceleration versus time graph, the change of velocity is equal to the area under the curve. Okay, area under curve. So the way you can look at this, remember, if I look at my definition of acceleration, it's the change of velocity over the change in time. If you look at a small increment in time and I bring that over to the other side, I have that the change of velocity should be equal to the area acceleration multiplied by delta t. So this equation right here gives me the change of velocity. So what would that mean? Change of velocity is always a v final minus a v initial. So when would I have constant? I'd have a constant if this guy here equals to 0. And the only way you have that is if acceleration multiplied by delta t is 0. That means I can't have any area under the curve, okay? So it really must be choice I over here. There is no area under the curve, so the velocity would be constant. All of these other cases here, I have, within this little block, I have a little bit of area. That means I'm going to change velocities here in that time interval. Also here, going from this time to this one, I have an area under the curve. Therefore, I have a change of velocity. Okay, so those three graphs are what we're looking for. All right, indicate all the graphs that represent an object moving with constant velocity. So let's be careful here. We have position versus time graphs. We have velocity versus time graphs, and we also have acceleration versus time graphs. How do we indicate constant velocity? So for position versus time, remember, how do you find velocity, right? The velocity represents the slope of the graph, okay? So what we're looking for is a constant slope, and the only one with a constant slope is choice A, okay? The slope is negative, but it's constant, so that's good. If I have a velocity versus time graph, and I want to have a constant velocity, well, the velocity has to be the same everywhere, right? So clearly this one here has to have constant velocity. These other ones here have velocity that is different for every moment in time. It cannot be constant. And the last one is acceleration. How do you find the velocity, or how do you show an object has constant velocity from an acceleration versus time graph? Okay, remember, if you have an acceleration versus time graph, the change of velocity is equal to the area under the curve. Okay, area under curve. So the way you can look at this, remember, if I look at my definition of acceleration, it's the change of velocity over the change in time. If you look at a small increment in time and I bring that over to the other side, I have that the change of velocity should be equal to the area acceleration multiplied by delta t. So this equation right here gives me the change of velocity. So what would that mean? Change of velocity is always a v final minus a v initial. So when would I have constant? I'd have a constant if this guy here equals to 0. And the only way you have that is if acceleration multiplied by delta t is 0. That means I can't have any area under the curve, okay? So it really must be choice I over here, there is no area under the curve, so the velocity would be constant. All of these other cases here, I have, within this little block, I have a little bit of area. That means I'm going to change velocities here in that time interval. Also here, going from this time to this one, I have an area under the curve, therefore I have a change of velocity. Okay, so those three graphs are what we're looking for. All right, find the average velocities for the time intervals A, B, C, and D. So these are the time intervals over here. And we have a position versus time graph. And we're looking for the average velocities. Now, if you're given a time interval over here, the way you find average velocity for any time interval is simply to evaluate delta x over delta t. Okay? And this is always x final minus x initial divided by the time interval that we're looking at. So let's evaluate it for time interval A, B, C, and D. We're simply applying the same definition. Okay, so for section A, this is what we're looking at. So we're looking at from time 0 all the way to this final point over here. So we started over here and we're finishing right here. So we simply have to read off those coordinates and apply the definition. So my average velocity over here, what is my x final? My x final is this guy. That is 3. 3 minus, and I started actually at 3. Oh, that's easy, over delta t. What is this time interval here? Time interval, I can read it, it's 4 seconds. So I have to get 0 meters per second. I actually have no displacement, right? Although I've done all of this, it doesn't matter, okay? I'm only looking at my initial point and my final point. All right, let's look at the next time interval. For time interval B, now this here becomes my initial. Let's switch colors here. This is my initial, and my final now is right at the end of that time interval up here. Now you can see I should get a positive slope, right? I'm really looking for the slope between those 2 points. That is really the definition of V average. All right, so let's go ahead and substitute in our definition. My final position here is 4, minus my initial position was 3. And what is the time interval that I'm looking at? It looks like 3 squares. Each square is 1 second over 3. So I get 1 over 3 meters per second. So a small positive value. How about C? So for C, let's get rid of this. For C, this here is my initial, and my final is right here. Okay, we're going to go ahead and apply our definition again. V average for that time interval. Again, it's my final position. My final position is right here, and that's minus 2. And minus my initial position. My initial position we said was 4. What is the time interval? Again, it looks like 3 squares over here from going from the initial to the final. So this is over 3 seconds. I have to be a little bit careful here. So I get minus 6 over 3. I get minus 2 meters per second. Again, that minus 2 is really simply represents the slope of this line that joins this initial to the final. What is the slope of that line? Negative 2 meters per second. All right, and my last case was time interval D. Again, this is my starting now, and my ending is over here. We apply the same definition of V average. This here is, so delta x, my x final is this one. That's 1. And then minus, my initial one was minus 2. So you see the way those negative signs here are going to cancel out for this case. My time interval here for section D, or for interval D, is also 3. So here I get 3 over 3 gives me positive 1 meters per second. And again, that positive 1 simply represents a line, the slope of this line that joins the initial to the final position. Okay, that's how you can calculate average velocities given a position versus time graph. All right, question 9 says we have a velocity versus time graph. First question is, what is the average acceleration for each time interval? Okay, so again, average acceleration, my definition here, is simply the slope of the graph, okay, if you're looking at a particular time interval. Okay, so pretty straightforward calculation. So we've got 1, 2, 3, 4 time intervals. Let's just do it for each one. Okay, so from A to B, how do I do this average acceleration? Well, again, you just do V final minus V initial over delta T. Okay. V final, let's go ahead and denote the 2 points here. Here's V final, here's V initial. So what is V final is 15 minus 5 and over delta T. Delta T looks like 3 seconds. So the average acceleration here would be positive 3.33 meters per second squared, right? 10 over 3. All right, a simpler one is from interval B to C. In that case, here's my initial and here's my final. You can see they are the same. So my average acceleration, or the average slope for those 2 points, has to be 0 because my delta V is 0. All right, how about from C to D? The average acceleration, again, V final minus V initial over delta T. And let's go ahead and denote my 2 points. So there's my V final. My V final for this case is going to be 0, right? Because I'm right here. I just read it off the graph. Minus V initial. My initial was 15 for that time interval. And then the time interval was 2 units, 2 seconds for this case. So the average acceleration would be negative, in this case, 7.5 meters per second squared. And the last one is from D to E. Again, if you just apply my definition, average, V final minus V initial over delta T. Again, the 2 points now are, this is my V final, and this is my V initial for that last time interval. So we get minus V final, so it's 0, and then minus, sorry, not 0. Oh boy, don't tell my boss. We get minus 15. It's my final velocity, and then minus 0, because that's my initial, and divided by the time interval. Again, it's 2. So notice we get the same thing here. So the average minus 7.5 meters per second squared. And you can see that right away from the line, right? The slope over here is the same as the slope over here. So I should get the same value. Okay, so that's how you find the average acceleration. Now they want to know, how far is the particle from its starting point? Okay, so what we're really looking for now in terms of a physical quantity is the displacement, right? That is how far you're going to be from the starting point. And how do you find the total displacement for this type of problem, right? So what is the displacement here for question B? Now, to get the displacement, if you have a velocity versus time graph, the displacement is simply equal to the area under the curve, okay? So what we have are, you can break things down now into nice straightforward triangles or trapezoids, rectangles, triangle, triangle, and simply add up the total area under the curve. So that's what we're going to do now for each of these sections, okay? So let's calculate the area under the curve for each one of those cases. So let me make some room over here. And we're going to now get rid of acceleration. And let's look at the area from A to B. So how do I find the area under this curve right here? What is this area? Again, what you can do, if it's a straight line, you can represent it by the average. This is just a trapezoid, okay? So the displacement from just this section over here is going to be 1/2 V initial plus V final. This here represents just an average value, right? The average value here is 10. Okay, and then you have to multiply by the time interval. Okay, the time interval here is going to be 3. So we substitute in our values. So you're going to get V initial is, 1/2. V initial was 5 plus 15 is for V final, and then multiplied by 3. Plug everything in, I think you get plus 30. Plus 30 meters is the displacement for this first time interval. Okay, let's look at the second one now. The second one is more straightforward. It's just a rectangle, right? If I'm looking for the displacement going from B to C, the area under the curve is simply going to be 15. That's the width multiplied by, that's the height rather, multiplied by the width, which is again is 1, 2, 3 units. So at the end here, you get a little bit more displacement. You get 45 meters for this section. All right, from C to D now, If I'm looking for the displacement, I am looking for simply the area under the curve right here. Notice I get a positive value again for this. And this is simply a triangle. So it's 1/2 base times the height. The base is 2 and the height is 15. So here you get a displacement of positive 15 meters. And the last section, let's go ahead and draw it out. The area that I'm looking for now is the area under the curve. Okay, again, it looks to me just like a triangle. So it's just 1/2. The base is 2. Now the height, you have to be a little bit careful, right? The height here is minus 15. All right, so at the end here, you get minus 15 meters. So how do I get the total? Well, the total, all you have to do is simply add up all of these displacements. So you get 30 plus 45 plus 15, and then you get minus 15 for that last case. So you can get rid of those. At the end, all you have to do is just sum those up. We get 75 meters is my total displacement for wherever I started. If I started at 0 meters as my initial position, then I would be 75 meters to the right of that position. Okay, so that's how you do that. So how about now if we sketch the displacements versus time on a similar graph, right? I'm going to label all of these points A, B, C, D, and E. So let me go to the next graph here. And so what I have here is I've created a position versus time graph. And I've listed over here also the displacements that we just calculated for each section. There was my 35, my 40, my 15, and my minus 15. So let's see, that means at position B, I should be right over here. Let's change colors here. I should be right here, and this here should be 30 meters, okay? Going at C, from B to C, I should be an extra 45 above, right? So this here should be 75 meters, okay, this line. And now if I go up to point D, if I add up all those displacements, A, B, and C here, the first 3 displacements, I get 75 plus 15. So I actually go all the way to 90 over here. And then what? Now I have to take away 15. All right, so now the question is, when I connect these lines here, what should I do? Okay, now you don't necessarily just want to put straight segments between them, right? Because look what you have here. Here you have a velocity that is changing. The velocity starts at 5. So it's some value over here, but it gets bigger. So that means that the slope has to get bigger. So it has to get bigger like this, okay? Make that a little bit bigger. And now what happens from B to C? The slope is always the same, okay? The slope is always the same. It's not the best graph, but that's what it looks like. Then what do we have? The slope, at least at point D, what should the slope be? The slope here should actually be 0, right? Because look at the velocity. The velocity equals to 0 right here. So this here must be like a maximum value. And the slope here has to decrease to something like that. And then the slope gets smaller. Okay? And then we're right back at 75 meters, which is what I calculated in question B. Okay, so this is kind of what it has. So it's curved upward here like a parabola, constant slope, and then curve downward like this because it's slowing down for that first section, right? And then changing directions and going back toward the 75 meters. All right, the last question for this problem says, when is the particle traveling the slowest? Well, that's obvious, right? It's going to be traveling the slowest right here, right? This is where the velocity is 0. That's right at the top. That's where the velocity is 0. Okay, so that was a pretty good problem. All right, question 10 says, if x equals to 0 at t equals to 0, write an equation for the position, the velocity, and the acceleration with the correct numerical constants in the equations. And you're given this information in the graph. So let's look at some important information over here. First of all, we have a velocity that starts over here. So this would be like my initial velocity in the x direction. What else? We know that the velocity is getting lower and it looks like the slope is constant, right? There is a slope, and remember what the slope is. It's the acceleration. The acceleration is the change of the velocity with respect to time. So we have v final minus v initial over delta t. So let's find a value of the slope here, and we're going to use that to build our kinematic equations to describe this motion. So VF in this case, VF is down over here, and that looks like it's approximately minus 50. Notice the acceleration or the slope should be a negative value, and then minus, what is the initial value? The initial value is 50, and that's divided by 10, right? 10 seconds is the whole period of time for this. So we get minus 100 over 10. At the end of the day, we get an acceleration in this x direction, which gives me minus 10 meters per second squared. Okay, so that's kind of an important equation. That is a constant value, right? So that is really this part right here. This part is the acceleration in the x direction. Now, if we go back and think about the velocity, now how would we describe this velocity? There is a kinematic equation, right? One of the kinematic equations looks like this, says the velocity, we're talking about in the x direction here. Let me correct that. The velocity in the x direction equals to the initial velocity in the x direction, right? Plus the acceleration multiplied by time. This is the equation for a straight line, and this is the straight line that I'm talking about. So if I do want to substitute my values into this kinematic equation, I'm going to get that the velocity as a function of time gives me, well, 50 is the initial velocity right here. And then the acceleration I just solved was minus 10. So I substitute that guy in here. And look what I have, an equation for the velocity in the x direction. Look at this equation right here. There is a time when the velocity is equal to 0, right? When is the velocity in the x direction equal to 0? Well, that would be when the time is 5 seconds. And 5 seconds is actually right here. You can see that velocity equals to 0 right here. Okay, when t equals to 5 seconds. All right, and the last one that I need is the position. Okay, we go back to our kinematic equations. The kinematic equations apply to cases where the acceleration is uniform. And in this case, the acceleration is uniform because the slope is constant everywhere. One of the kinematic equations looks like this. It says that the position equals to my initial position plus the initial velocity multiplied by time, and plus 1/2 the acceleration multiplied by t squared. Now everything we're doing here is in the x direction, so I could add some subscripts here. All right, what is the initial position? What is this guy? For that, you have to go back to the initial condition right here. And they told us that when the time equals to 0, the position should be 0. So that's pretty straightforward. That case is 0. The next term we know, it's the initial velocity. So the next term is 50 multiplied by t is a variable. And then what do we have? Plus 1/2. And the acceleration I should put is minus 10 into this equation multiplied by t squared. So if you plot now, if I just continue this, just clean this up. The position as a function of time is 50t. If I just take this division here, I get minus 5t squared. Okay, and this is my equation that describes the position for this particular graph, right? So at every time I could calculate where this particle or where this object is as a function of time. All right, that's it for me, folks. Thanks for watching.